Welcome back, everybody. Today, we're going to be talking about what the heck dx and dy and d whatever. What is d? What is d? Right? Now, in my last two videos, I brought up this notation, this d over dx of f of x. And I used that to say taking the derivative of f of x, right? I said that it's equal to f prime of x, but it's also equal to df over dx. What could that all possibly mean, right? I realized that I was using that notation, just kind of telling you that that's what that means, which is exactly what I'm trying to avoid, is just telling people how to do things without telling them why it works or what exactly is going on behind the scenes. So that's the goal of this video. To start, we need to think about what a derivative exactly is. A derivative is the slope of a function at any given point on that function. So you have a function, maybe it looks like that. The derivative will tell you at this x value, the slope looks like that. At this x value, it looks like that. And at this x value, it looks like that. And it works for any x value across the entire function. All right? So what does that exactly mean? It means that a derivative has to be defined in terms of slope. And slope, this is classic, change in y over change in x. Remember this triangle, delta, it just means change in. So slope is change in y over change in x. Now, that looks very similar to something like dy dx. So what's the difference between this delta and this d? Well, if you recall, the differential of a function is this limit, where we have change in y over change in x. Remember, f of x plus h minus f of x, and we're getting the change in y to be as little as possible by making h as little as possible. So we take the limit as it approaches 0. And on the bottom, remember we have that x plus h and then minus x, but these just cancel to leave out h, right? So we have change in y over change in x, and the derivative is just making the change as small as possible. We'll consider something like y equals 2x. This is a linear function, right? It's just a line. So the derivative of it is going to be a constant. In this case, it'd be 2, right? Because the slope at any point is equal to the slope everywhere, because it's just a single line and it's just one slope, and that's 2. So the idea is we have a change in y and a change in x. So we're going to consider x first, right? Maybe this is our change in x, all right? From 0 to this point, we'll call it h. Which means the equivalent change in y, maybe we'll call this g, the equivalent is going to be, I kind of drew this poorly, but h is going to be 1/2 of g, because x is always going to get doubled to get to y. So h equals 1/2 g. Or, do a little bit of algebra, we get g over h equals 2. Okay, so g over h equals 2, that's simple enough. But what happens when we make g and h smaller? The relationship won't change. G over h will always equal 2 because this is just a straight line and the slope is the same everywhere. But if we make h infinitely small, then its corresponding g will also have to be infinitely small. Even if you multiply it by a billion over infinity is basically the same as 1 over infinity, right? It's a drop in the bucket compared to infinity. So, as you shrink g and h, we'll consider our h. As you shrink h, it gets infinitely small. We have an infinitely small change in x, which is what we described dx as. And it's the same thing for g. When you shrink it, it's an infinitely small slice of y, which is our dy. So we see g over h will equal to, in this case for the whole thing because it's linear, but specifically in the limiting case as we get h super close to 0 and g super close to 0, we'll get dy dx, because again, dx is just a tiny little chunk of x, and the same thing for dy. So this is equal to 2 for our y equals 2x function. Now we consider a nonlinear function, something like y equals x squared, right? Now the change is different. The slope is different at each point of x. So we choose a point, x, choose a second point, x plus h, f of x plus h, and we just want to minimize this to find that infinitely small slice of x, that being dx. So we want h to approach 0. Hey, wait a second. Surprise! It's just the difference quotient. dy dx is really just the difference quotient. We have an infinitely small slice of x, which is just going to be 0, or at least the limit as it approaches 0, and an infinitely small slice of y, which is related to whatever that infinitely small slice of x is. Even though they're both infinitely small, it's a different size of infinitely small, which doesn't really make sense because 0 is equal to 0, and if they're both approaching 0, how are they not equal? But they both approach 0 at different rates, which is an important thing to consider. And we can see that here. F of x plus h minus f of x, if we just plug in 0 for h, we'll get 0 over 0, and that's not helpful. But the trick lies in that it's different rates at which they approach 0, which gives us an overall rate, which is what a derivative is. It's just a rate of change, because that's what slope is. It's a rate of change. dy dx is the rate of change as dx changes compared to how dy changes. That's all a derivative is. So all this fancy notation about d dx is just saying, what infinitely small slice of f of x do we get when we take an infinitely small slice of x? That's what it means. Thank you so much for watching.